actually started, yeah, we started also with the text bit of it, and we're going to continue with it. So we're going to look at the text, the image, the sound, and the signal. These are, you know, the major form that data can be accessed by a system. We talked about the I/O, that's input and output, and processing. So we're going to look at all those today. Now, having talked about the text, I told you people that the code, started with what we call ASCII, which is American Standard Code for Information Interchange, meaning that there is a way of codifying some of the signals. Remember, we're talking about electrons flying around. I showed you what mode bus looks. Sorry, not mode bus. What a bus looks like. A bus carries information, from one area of the system to another area of the system. Now we're going to be looking at, when we talk about signals, ones and zero, you now understand, how the system interprets every single thing we do, from transaction to watching videos, from watching videos to playing games, a lot of things, manipulating different software, everything boils down to one and zero. So the place we start from is the ASCII. So ASCII, of course, I've told you the meaning. It is actually limited to 127. Yes, 127 characters. You can see it here. If you see number one is null, zero is null. Two, it starts from the heading. Like I said, zero in ASCII is not zero in our natural world. You can see that the zero in our natural world is actually assigned to the number 48. If you look at the slide very well, if you check number 48, so that's zero. So when you actually type zero in your system, what does it actually signify? You can see different characters there, but now you might be wondering why it is limited to 127. Okay, so I'm going to continue from where I stopped last week. So let me just bring in this slide. Okay, so like I said, I'm going to break this thing down from the known to the unknown, what all of us understand. Okay, so you know that decimal, okay, this is decimal, it's called base 10 for a reason. So because decimal is called base 10, you could see that each box in the decimal, stands for something. So you start from the right hand side, you have U, which is units, and then from units you go to 10. From 10 you go to the hundreds, from the hundreds you go to the what? 10,000. What it means is that any number you put in that box, in the first one will be multiplied by 1. Any number you put in the second one will be multiplied by 10. Any number you put in the third one will be multiplied by 100. Of course, we all understand this, in normal parlance. So it continues like that. Of course, this is not exhaustive. You have your 10,000, 100,000, then 1 million, 10 million, 100 million, and so on to billion, trillion. So, but if I teach you this fundamental, you can understand, the other part of it. So now, this thing equally means that, okay, there are 10 possible, when you talk about decimal and base 10, aside multiplying by 10, that means you see now, you have 10 possible things that can occupy that particular position, right? So you can see I listed them there, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Once you reach this 9, you move over to the next one. You remember our normal addition, carry one, carry one, carry one, all those things, is because it's base 10. So you cannot put anything. 9 is actually the highest thing that can occupy that particular position. So if you put 0 in that unit, it means times 1. Okay? So 0 times 1, 1 times 1, 2 times 2, 2 times 1, 3 times 1, 4 times 1. So it doesn't. But if you move over to the next one, you understand, where you have T, that's 10. Anything you put in that box means times 10. If I put 1 there, right, it means it is 1 times 10. So what, even though it's just a single number you're adding in that box, but it means something as far as it's occupying that second position. If you move over to the 100, if I put 9, it means 900. You understand? So that's what they call number representation, right? It's 900. If I put 7 in the thousandth this thing, it means 7,000. So you could see, how did we start? We started from 1 in the rightmost corner. Then as you are moving, you multiply 1 by 10 because it's base 10. You now have 10. 10 multiplied by 10, you have 100. 100 multiplied by 10, you have 1,000. 1,000 multiplied by 10, you have 10,000. 10,000, and so on and so forth. That is how this thing grew. And that is the understanding of base 10, right? So for me to move from the known to the unknown, now we are going to now go into binary. Now look at this, binary is base 2. You see? So exactly the same thing, because sometimes these things, you might cram it, you might not understand. If you check the philosophy and the logic from the last slide, if you apply it into this slide, you understand the place of binary and the computer code. If you don't understand this, then you don't have the fundamental of IT. You understand? So if you look at this also, the last part of it is what? It is binary. Okay, as you can see, its binary is base 2. Okay, now let us start from, let's move start. When it's base 2, when you are going from the right to the left, you're no longer going to be multiplying by 10. Because it's base 2, you're going to be multiplying by 2. So you have 1 there, 1 times 2, you have 2. 2 times 2, you have 4. 4 times 2, you have 8. 8 times 2, you have 16. 16 times 2, 32, 64. Just like the other one, this one is equally not exhaustive. You're going to see, the demo very soon, okay? But unlike the other one, okay, the possible thing that can be in each box is only 1 and 0. The other one, if I go back to the other slide, you see that the possible thing that can be in one box is 1, 2, 0. You start from 0 and end in 9. That's 10 possible things that can be in one box. But when you're talking about binary, you have only 2 things, 1 and 0. You cannot have 2. You understand? So it's binary. Just like we have 9 as the highest in the other one, 1 is the highest in this particular one. So 1 and 0, you move over to the other one, and 0, you move over to the other one. So you could see, if you follow this logic, it's very simple to understand. Okay. Again, there is something, we need to look at here. Okay. Now, we are going to now go back. Let me go back to the slide. You see that these characters, right? Even though it's in base 2, there's always an equivalent that you can translate. Is it translate? Okay. Is it translate? There's this convert. Sorry, that's the word I'm looking for. You can convert from base 10 to base 2 and base 2 to base 10. So there's something representing the base 2, what ASCII does. So everybody listen to me now. What ASCII simply does is to ensure that there's a way of representing the thing in base 10 also in base 2, right? So that every single signal will be unique and will not be repeated. So that when the CPU receives a particular signal, it will obey a particular command. Okay, that signal could be a number, that signal could be equally another command, that signal could be an operator like multiplication, division. Multiplication will have its own series of ones and zeros. So I want to begin to explain to you how this 1 and 0 actually works. Ladies and gentlemen, your computer does not understand A, B, C, D. When you have your keyboard and you press A, it sends a bunch of signals. The way the signals are sent to this thing, CPU understand the particular character that is assigned to those signals. And we are going to demonstrate it right away. So you can see we have A, B, C, D, and all that. So we are going to, let's just do like a simple demo. Okay, let's go to like a simple demo now. Now, assuming we are using ASCII and we, example, want to spell the word code, okay? If you want to spell the word code, now, this is where we left off last week, right? Now, the first thing we need to do is that C, right, is a character, and that character is not understood, at the machine language level with the natural distinct, okay? So I'm not going to now do this. Somebody says this is where we stopped last week, actually. So you've not lost anything. So now the letter C, okay, just follow me, has series of what? Ones and zeros, which is binary. Binary means two. You're not going to have any representation. So O, D, E. So this is capital letter C, capital letter O, capital letter D, and capital letter E. So let's go to the ASCII, right? Let's go to the ASCII. Capital letter C, okay, follow me here. You can see that C is what? 67, okay? Follow me also. O is 79, okay? So let me go back. 67, 79, okay? 67. So we're going to do here, this is going to be what? 67, okay? O is what? In ASCII, it is 79. Okay, let's go back to that ASCII table again and find D and E. Okay, capital letter D is 68 and capital letter E is 69, 68 and 69. So let's complete it. So 68, 68, and then we have what? 69. Now, what I wrote here now, close to those letters, is the decimal 68 and 69. So this is the decimal representation according to ASCII standard, right, of CODE. So what we are trying to do now is when you go to your keyboard and type capital letter CODE, I want to show you what is actually sent to the CPU that makes it print those letters on your screen. So first of all, the first one is what? 60. Let me zoom in a bit. Sorry. Okay, so let's work with this. Now, remember what we said, right? Of course, you have seen how this 1, 2, 4, 8, 16, 32, because of binary, I've explained it very well. So there should be no confusion there. So we are moving forward. Now, 67, right, we are going to ask ourselves, you can see CODE, they are unique. None of them is repeating. Forever and ever, capital letter C, as far as computer is concerned, is what? Decimal 67. Note it today. Forever and ever, the capital letter O is 79. That's why it's called standard. It does not change. So let us take C. Now, if, okay, remember we talked about on and off, right? On and off. So what is going to happen is that I want to ask everybody, and I want to probably see some response in the chat. What combination of these numbers on top, right, will I add to get 67? Can people just, I want this to be interactive quickly on the chat. How can I get 67? Because C is 67. What combination of this number 1, 2, 4, 8, 16, 32? So let me see on the chat. Okay, somebody said 64, 2, and 1. Very good. 64, 2, and 1. 64, 2, and 1. Okay, we all agree it is 64, 2, and 1. So what we are going to do is that we're going to on 64. Okay, let me use yellow to mean on. Okay, on 64, we are going to on 2, and we are going to on 1. So every other thing will be off. So what we are going to do now is that anywhere you see yellow, it is 1. Anywhere you don't see yellow, it is 0. So this is the combination. So for this, I'm going to rewrite this thing to become what? So it's going to now be 1, which is the yellow. The next one is 0, 0, 0, 0, 1, 1. So that is capital letter C. Okay. So thank you for those that participated in this. Now, can you still hear me? Can someone confirm? Okay, thank you. Thank you. So now we're going to do capital letter O. So I want us to participate. Can you give me what combination of this number on top? So let me off all of them now. Let me off all of them. So give me the combination that will give us 79. Everybody quickly on the chart. So somebody said 79 is 648421. Okay, that's Mary Jane. Onyekon, thank you. Any other person? 64821. Okay. Chibweze, the difference between your own and Mary Jane is that Mary Jane has 4. Okay, let me have more opinion. Okay, you have added 4. That's very good. Who again? So you are agreeing with Mary Jane. Yeah, Allen eligible 648421, 6484. If I get that one is correspond, I don't need to, confirm again. Any other person, 648. Abiola, there's no for your own. Oh. Ijoma, 64841. So I am agreeing with 64. Okay, 64. So we are going to what? 64 on. Okay. 8 on. 4 on. 2 on. And 1 on. So I'm assuming that people are correct though, because I don't have time to probably check all this, right? But I think the principles are understood. So this second one now, is it going to be, what is it going to be? It's going to be 1001111. Okay? Yeah. So everybody, let's do the third one. D is 68. Can I have 68? Okay, someone says 64 and 4. That's, I can even calculate that one. Also 68 and 4. So I'm going to, put off everything. Okay, Abiola, thank you. Doris, thank you. Michelle, thank you. I can see. Alan Elochuku, thank you also. So it's going to be what 64 and 4. So I'm going to on this, and then I'm going to on this. So the combination is going to be what? We're going to have 1000100. So the last one, 69. Okay, Mitchell 641 641 641. Okay, so 641. So we are going to, sorry, 64. 64 4 and 1. Sorry, 64 4 and 1. So 64 4, and then I will not split all these ones again. Just, I think the point has been made. So in this case now, what are we going to have? We're going to have 1000101. So now let me zoom in. You see that these letters are unique and they cannot be repeated. There is no way, if you are using this standard. Ladies and gentlemen, that's what we call machine code. So plus has its own, minus has its own. So if you say 2 plus 2, you send a bunch of ones and zeros to the CPU first. Then the second signal will be plus. So there's a signal for plus, you send it. Then the second number, 2 plus 2, you send another set of signal. When you click enter, the computer knows that this middle one is an operator. So that's how it works. So those that were wondering how the programming, giving instruction and everything, that's how it works. Now let's go further. So what you understand now is, let me go to the slide, go back to the slide. You can now see, okay, for those that might not understand why they say this is limited to 127, right? Let me go back to this thing. I'm going to answer that question now. I want everybody to check, okay, if I on all of them, right? On this, on this, on this, and on this, okay? Everybody, if I on all of them, what number do you think will be? Because it is now, everything is on. So you're going to do 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64. Somebody will give answer. Okay, so 128. Good. Now, 128. So you now have 128. So you could see, if you go back to this code now, you are going to see that, okay, we have from 0 to 127. 127 is representing delete, okay? So 0 represents null. Now, the question is that everything in this world, does it end with these characters, the capital or uppercase letter of English alphabet and the lowercase letter of English alphabet, the answer is no. So, ladies and gentlemen, that brings us to what we call Unicode. Okay, they call it Unicode Transformation Format. You are going to see UTF. So these are the terms that you need to know as a tech person, right? Why Unicode? You will ask yourself, what of signs? What of Greek alphabets? How do you represent them in a system? So at some point, this came up, for people that are building the standard. So they realized that this 128 to 127 is not going to cut it. So we need to begin to what? Increase this. So because of that, Unicode, for those that don't know, right, is equally standard as well. So what happens is that they've now integrated Chinese language, Japanese language. Every single sign in the world contains unit code. And when you see UFT8, it means that that 7, okay, is now 8. You now added another box 8. But we have not stopped here. Remember, now we have different emojis, right? Remember the emoji, you are still typing it in your system. You are still typing it in your phone. So when you say smiling face, what does it actually mean? It means that those particular characters, those particular signs, those particular symbols equally have its own ones and zero. And if it's going to have its one and zero, then we have to expand, what we actually have. So, ladies and gentlemen, this is what we now have. Okay, let me just give you an example. So if you come to this now, you see that Unicode now, you can see there are some of these boxes that are now colored differently. So when you add a single box, right, you have added more possibilities. That's what I'm trying to say. You are going beyond the 7 bits. Remember, we defined bits. Each of these boxes is a bit. Okay, so each of these boxes is a bit. If you add just one bit, you have added more possibilities. You understand? Because right now you have, if you add 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64, now plus 128, in case it is 8 bits that you are talking about now, you now have the total number, because at that point you're going to on all of them. To know the highest, you just have to put all of them on. So you can see you have moved to 256. We now have if you put what is simply happening here, don't get confused, it's simply being multiplied by 2. Okay, so I think at this point I want to point out something. Have you noticed also that the storage devices that we have, the memories, okay, because we started like this, the computers society also have decided to maintain the same kind of nomenclature. That is why you're going to have 2 gig RAM. You will rarely see something like 3 gig RAM. You are going to see 2 gig RAM, 4 gig RAM. I know most of you have not asked yourself, where are these numbers coming from? 8 gig RAM, 16 gig RAM, 32 gig RAM, 64, 128. To even in your phone, go and check. You see, somehow, to make things easy, there's nothing so special about it. They just want to keep things, very simple for people to understand, and not try to cram different standards for different things. You understand? Even in SSD today, you're going to see SSD 521. So people, why is it 521? Why is it not 500? This is the answer, right? You're going to see SSD 256. Your phone memory. Some people will buy iPhone. They say your internal memory is 256. Your own is 128, or some of your own is 64. Even in flash drives, also, you see similar thing apply. In flash drives, all those things. So you rarely have all these things. So you can see these things, they didn't just drop from the sky. These are just standards that we keep maintaining, right? So now, having said that, let's move over to, it's not only text. You can see these are different things. Decimal, you have one. The first one was 0 to 127. You can see you have added from 128 to 255 and all that. You can see a lot of things have been added. Geometric shape, oh, drawing box, oh, arrows even have their own. Currency, you can see that currency have their own. So don't be surprised. Don't be wondering where all these things are coming from. This is the reason. Computer does not understand anything aside from 1 and 0. The only way it's going to understand your angry emoji, your smiling emoji is having a unique set of 1 and 0. That's what is happening. So if everybody is allowed to adopt different standards, there will be chaos in this IT world, right? So there's what they call hexadecimal as well. Hexadecimal is you have your decimal and you have your alphabet. Hex, what first six letters of the alphabet. But we are going to come to that very soon when we talk about even colors. Now, having dealt with text, let us move on to colors. How does your computer understand image, game graphics, video you are watching, and all those things? We are going to break it down now. Okay, this is still 1 and 0, right? We are still using the same principle. In this case, I want you to understand that for colors, right, there's what they call, so we are going to be combined, just like we did biology in the first class. We're going to be coming all the fine art again. In fine art, you have primary colors and secondary colors. Even in primary science, I want to bring those memories back, because sometimes you leave these things, but they mean a lot. So I want to bring us back. Primary color simply means RGB. Again, when you hear RGB, you see RGB somewhere and all that. I'm going to connect all the dots now in a clear term without any ambiguity. R simply represents red. G simply represents green. And B simply represents blue. All other colors in the world, okay, is a combination of these colors in different proportion. If you also come to physics, okay, when you talk about color prism, when you pass a color through a prism, there's what they call, I can't remember the name now, is it dispassion or something? So it gives you that rainbow. You see, there is no thin line or district or sharp transition of color. You see, it kind of, goes from one color to another color and everything. What it means is that when it passes through that prism, there are different, they call it a spectrum, and no light wave has a unique, what we call frequency, the visible, that's what we call visible light, because there are other waves that are not visible to the eye. There are other waves that are not even audible to the ear. Sometimes like you have rock beef and all, but this is not physics, right? So when we talk about colors now,
You are stealing my things.
absence, I'm hearing a voice.
Carry
Okay.
this thing,
So,
please. When you
okay. So, now you see, let's take R. Okay. R has value from 0 to 255. Look at it. It's looking at you now, staring at you. Now, G equally has value from 0 to 255. Okay. O has value from 0 to 255. Now, if I want to, all the colors you can ever imagine, all I need to know is what portion of R will I take and combine it with what portion of G and combine with what portion of B. If you can see in this slide, okay, hello, please confirm you can still hear me. I'm seeing some strange stuff on my. I need voice now.
Yeah, we can hear you.
Okay. All right. Okay. Let me just continue. So, ladies and gentlemen, if you observe carefully, if you take 0 of R and take 0 of G and take 0 of B, I'm going to get dark black. Okay, so if we have 255 of red, and I take 255 of green, and I take 255 of blue, if I combine them, I'm going to get white. Combination of all the colors will give you white. Okay, absence of all the colors will give you black. Okay, so now the idea of pixel, because we are now going to translate it into what we understand. When you display a picture on your phone, that your picture is divided into very tiny boxes. In fact, you can call it a dot, right? So those tiny boxes, we assume different kind of possibilities of colors running into millions. Okay. Now, when you display it, that's when you see your picture, because when you combine all of them, you now see your picture. Let me go to video. Video is simply a moving picture. So if you can understand picture, video is just like pictures moving through time, different pictures moving through time, being displayed. So you have what they call motion. That's why the film industry started what they call motion pictures before they started using the word video. So what do you understand by motion pictures? Now you understand what is happening, right? Now, a pixel is simply means what? Picture elements. So pixel. Oh, iPhone. Everybody's buying iPhone. This is a pixel. This one pixel. Everything. It shows you the resolution of the quality. Is the resolution is actually quality. Shows the kind of resolution that you're going to have. So what you're going to have here is, let me take a pixel. You can see that tiny dot. Okay, we have made it pink in this particular picture. So assuming I want to get that particular pink, right? Okay, so pink is not a color on its own. So pink is a secondary color, which is gotten from different combination of the primary colors, right? So how did we get pink? You can see the hexadecimal is hash FF69 and B4. You are going to see most of you that are going to be doing UI UX design, color picking and blah, blah, blah. You are going to play more with this thing as well. And I'm sure also when you give your design to a developer, the developer will be able to interpret it and choose the exact color that you use. In softwares today, you have what called color picker. What the color picker simply means is to pick the exact, the combination of it. Now, for us to get pink, right? An example is given on this thing. We need extreme red, which is 255 red. So for you to get 255, okay, I'm not going to repeat that box 1 and 0 again. You know that for us to get 255, okay, we have to add 1 plus, just follow the logic. 1 plus 2 plus 4 plus 8 plus 16 plus 64 plus 128. Okay, I hope you guys get it. So I want to pull up this thing now. Okay, where is it? Right. So look at this now. If I go to the next one, this is red. Okay, so you ask yourself, R. Okay, how do we get R? I'm going to on this, 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 and then on this. Okay, I'm owning all of them. In this case, it's going to be what? 1, 1, 1, 1, 1, 1, 1. Okay, so if I go to this slide, you now understand where this 1, 1, 2, 3, 4, 5, 6, 7, 8. My own up to 8, so let me check. 1, 2, 3, 4, 5, 6, 7. So 1, 8. So this box is how many? 1, 2, 3, 4, 5, 6, 7, 8. So guys, ladies and gentlemen, we have selected this particular. I just want to show you how this 1 and 0 equally translates to color. Please definitely translate to your images. Now, the next one is what? The next one is what? G. Okay. So let's go back to this thing. So the G we are looking for now is 105. Okay, 105. So 105, how do we get, okay, if I go back to this again, you need to ask yourself, please, what combination of this can I do to get 105 so that you guys will understand where I'm coming from? And we do that quickly, the smart ones, I know saying not be everybody like gets this thing. So can you quickly just on the chart, how do I get 105? One oh five, 105, 105, 105. Okay, somebody says 64, 32, 8, and 1. So let me say, let me assume that he's right. That's Allen, Mary Jane also 64, 32, 8. Okay, now Udo, I'm gonna say okay. All right, so 64, okay, 32, okay, then 8, and then 1. Okay, so what we're going to have here is 0, 1, 1, 0, 1, 0, 0, 1. So let us go to that listing. Guys, have you seen how we got this 0, 1, 1, 0, 1, 0, 0, 1? I hope it's clear. So now I don't need to do the third one, which is what? 8, 180. So we got a combination of 255 of red, 105 of green, and one. When you combine them, look at this end. You can see you have 1111111, 011010001, 10110100. This is what the computer. This is for that small pixel, for that dot that is pink. And for us to demonstrate it, let me just use PowerPoint because PowerPoint equally has some design tools, right? So let me create a box, right? Let me create a box, right? Right has entered my mouth. Somebody taught me, right? All right, so okay, see what is going to happen, ladies and gentlemen. So I have drawn this box. Let's see if these colors, right, will give me pink. This is a demo. This is a live demo. This because PowerPoint equally has, designed this thing. So I'm going to click on this, but to color it, even though we are still going to do PowerPoint in the application, sure. But let me just show something. If you click on this, now I'm going to choose more colors, right? So when this thing comes out, some people will be asking, what are these? What does all these things mean? Right? What does all these things mean? So ladies and gentlemen, see what I'm going to do, right? In this thing, okay, this thing you are seeing here for red. Now this thing is going to make sense to you. I'm going to type in 255 inside this box. Okay, I'm going to type in 255. So I'm going to see if this is going to give me the pink. The second one is 105. The second one is 105. And then the third one is 180. So let's see whether it's visible of pink. 180. And then I'll say, okay, voila. You see, pink. So when you combine red of 20, so you can see how all the colors on the world, is arrived at. You can see when you combine red of 255, G, that's green of 105, and the other one of 180 is going to give you pink. So this is, live demo of everything. So we can see I don't need to repeat this again. Now let's go back to the slide. So what it means, if I go to the next slide, to give a concept to it, okay, this is what it means, to demo what pixel is actually. You can see that each of these dots can decide to take any color of its own. It has possibility of taking a lot of color. And these colors, you can see you have 16,777,201 216 possibilities in each dot. So why can't this thing give us all the pictures in the whole world? If each dot can have this, so combination of shades and different colors, each pixel. Sorry, hold on. I need to share my screen again. Somebody say hot pink. Yeah, so even though I know this thing, but these days when they invite you for a wedding, you see very strange colors, marine blue, very interesting. Uh, Let me share my screen again. I think we are back up. So please confirm that my screen is visible now. Okay, thank you. So you can see what is happening here is that you have possibility of having different colors, right? And then Pixel can take any value for any image, for whether it's an image or video, right? So resolution. Now let's talk about resolution before we go over to the next one. So when you hear resolution, what it means is that what is the matrix? Matrix is something like just imagine rows and columns. Like if you have 5 rows and 5 columns, you are going to have 25 possibilities, different boxes. Just like if you are drawing a mesh or a table, something. So when you talk about the resolution, so when you say this by this, it means the number of feet, stretched out against the length and then the height. So what it means is that the display that you see when you have a higher resolution, it means it's going to contain more pixels. It's as simple as that. Because if you multiply this number of resolutions, the first one will be less, the second one will be higher than the first one, then the last one will be higher. So let's take an example. An iPhone 11, okay, has a resolution of 1792, okay, by 828. It means that the pixel, okay, the smallest dot, the combination of the pixel that is displayed in an iPhone is 1,483,776 pixels. That's a lot of pixels. So you could see, we have, come a long way in this whole thing. So let's move ahead. Okay, so ladies and gentlemen, when you see a beautiful picture like this, I want somebody to say, please send me that picture. The person is not actually sending you a picture. The person is sending you a bunch. That thing you see on the left hand side is what is leaving the phone, whether you are using Bluetooth to send, or whether you are using what's the other technology? Infrared. There was time we used to use infrared. Now we are having Zenda and whatever. Even if you are using WhatsApp, even if you are downloading it from Google and all that, what actually is being downloaded is a bunch of ones and zeros. So you are not actually transferring picture from one phone to the other. You are transferring these codes from one phone to the other, these signals. So when it reaches the phone, it will be what? Reassembled the way it came. So I want us to understand that. So moving forward, let us talk about sound. We have talked about text. We have talked about video. It is time for us to talk about sound. Okay. Now, for us to talk about sound, we have what we call amplitude. Okay. So as I'm speaking to you, right, you are hearing not exactly what I'm saying, but you are hearing a digital form of what I am saying. That's how the microphone works. And the microphone is, built to convert. Remember, I have mentioned analog signals. If you are staying with me in the same room, your ears, right, will be hearing everything, the analog signals, because when I speak, what I if you do that are familiar with physics, you have compression and rarefaction. What I'm simply doing is to manipulate the air between us to produce a particular sound. So it will come with different wavelength and frequencies and all that. pitch. There are different characteristics of sound, resonance and all that. So, but we are not here to teach physics. Now, when you do that, right, to a microphone, what the microphone does is it samples, what you are doing, because microphone, is not built to take analog signals, because analog signals are many. So the best we can do, for instance, you can see an example there. You can take 44,100 sample in a second. That's a huge, but that's equally sample. That's not the original thing. So you can take 44,000 in a second. Though. So in a second, what is going to happen now is that I am speaking, it's taking my wavelength. So the wavelength, of course, it covers all frequencies and pitch and all that. So even when I'm singing, even when I'm talking and everything, sounds can be represented in wavelengths. But in the actual sense, those wavelengths, when you're talking to a microphone, some of them are converted to voltages, right? So they have equivalent of wavelength. Then the speaker is able to produce that. You are hearing what I'm saying from your speaker. Your speaker is actually producing a sampled version of what I'm saying. I know some of you were like, how? It's as simple as that. So there's what they call audio to digital converter. They call it ADC. That's what you're looking at there. So when the thing comes, after sampling it, the audio to digital converter will turn it into ones and zeros to represent the particular wavelength, using voltages. That is how you are able to hear people on the microphone and all that. Is still ones and zeros. You understand? So a video that have audio is still, you're now combining colors also at the one of ones and zero. So ones and zero here is not representing pixel. It's not representing character the way we had it in text. Ones and zero in this case representing, different wavelengths, So that's how you are able to, hear what I am saying. So the job of the microphone, which is an input device, is to do this conversion. So the speaker will never produce, just any what you are producing from speaker, what you are hearing is like a sampled version of water. But truth that if you look at this thing, right, the red dots are the sample, right? Even though it does not measure every bit of it, but the red dots, you can see the way and the trajectory of the red dots still have a representation of what the actual thing is. That is why you're hearing me very well. Okay, so there's no need measuring every single tiny bit of it, but you can sample it and it will still produce something that resembles what I'm saying. Okay, which is, I know you're hearing but what you are hearing, what you are hearing is not exactly what is coming out from my mouth. What is coming out from my mouth is a continuous analog signal. So, having said that, okay, let's just now talk about. We have talked about how the thing comes in. It is time for us to now talk about when it comes to the system through your bosses and everything. How do we kind of process it? So we're going to talk about processor. Remember, after processor, we're going to talk about uh, storage devices. Okay. So, but today we might just to mention, we might actually end on time because I just did some procedure, so it might not allow me to talk for a very long time. So I just want to make sure that we kind of grab it. So I might just, because this is a continuous thing, we are going to be doing DAIPODs to the end of to the end of KodeCamp this year. So I just want to ensure that we grab. So I will go a little bit further. I just had a medical procedure today, so I'm just going to cut it a bit short. So, but let's talk about machine cycle. I can't end today without really delving into machine cycle. If I delve into machine cycle, I think I'll be satisfied because you guys really need to understand how these things work. Like I said, if you see, follow the story, you don't need to cram anything. If they woke you up from sleep, you'll be able to explain, and this is what gives you confidence in the whole tech thing. When you are doing your design, when you understand when they tell you optimize your code. We are going to look at what we mean, without any ambiguity. Now, if you look at what is actually happening in the microprocessor, because we've talked about, we are not going to dwell in vacuum tubes and integrated circuits and everything. Let us look at the computers we are using today. So I told you people that there are three key components of the CPU. Memory, which is primary memory, people call RAM. We are going to look at we have cache, we have register, but it's coming up. Now, what really happens in the machine cycle is that if you can memorize this acronym, FEDES, like FDES, that's all. You can go home and say, I know what CPU is doing. Okay, this FDES is simply what we call, some people call it cycle, execution cycle, some people call it instruction cycle, some people call it FDES cycle, some people call it machine cycle, whatever cycle it is. Please, what happens is that first of all, the machine fetches information. It's very even easy to understand. Okay, because the information you have to fetch it from somewhere. So the machine fetches the information. To decode it, right? So the decoding, so fetching instruction is like maybe from a memory, from storage. Some information equally come from I/O devices. I/O means input output. So when my mouse is moving, right, the CPU is equally working. It's part of the fetching. So information will come from somewhere. The next thing that's going to happen is that it will be decoded. Decoding means, okay, there's instruction that follows that information that is coming in, and you need to assign if that instruction is for the keyboard, if it is for the screen, so you need to understand what the command is, okay? It translates the retrieved information into computer commands. That's what is written there in the tip, this thing. Okay, so of course, if you translate, this is very easy to understand. If you fetch and decode, and that decoding, remember the outcome of the decoding is translating it into command. Then what is the next thing? Execute the command. Simple. Okay. So when you execute the executing command, is simply assign task, undergo the assigned task, undergo execution, and reach the output, port in the binary form. And of course, the last one. So FDES is simple. Then you store, right? You fetch, you decode, you execute, and then you store. This thing that you see here is what we refer to as clock cycle as well. I am heading somewhere, okay? Because sometimes when they jump into these definitions, okay, core I7, core I7, just follow this. You understand that those things are not very difficult to understand, right? So this particular cycle has been improved over time. We are going to look at it. Early computer processors needed to wait. They are what they call queuing. You queue on, like you stand in a queue and wait for your turn, right? But in computers today, we have what we call pipelining, which we are going to discuss in the next couple of slides, right? Pipelining has to do with having multi-threads, multi-processors, multitasking, all those names. Don't worry, we're going to look at it. Let's go to the next slide. Now, CPU spec. I want you to understand how this processor cycle, okay? You can see you have control units, ALU and the memory. You can see how they relate. So the control unit is the one that is fetching, is going to organize and schedule all this thing, pass it to what it is going to decode. So you can see the control unit decodes that information and gives it to the ALU to execute, right? ALU executes and then store it back in the memory. And from this memory, it's, could be stored permanently in the system, okay? When, of course, we store it, we are going to talk about storage devices very soon. All right, so let us talk about CPU. Please follow the logic. This is very simple. That thing I mentioned, that cycle I mentioned, you need to ask yourself, when you see, I bought a computer, it is 1.2 gigahertz processor. What it actually means is that you see that cycle, that your computer have capability. Okay, you can see You have 6 gigahertz here. You have 12 gigahertz here. You have 25 gigahertz. Gigahertz simply means what? Machine cycle per second. Machine, that cycle I just showed you, how many of it can happen in a second? So when they say computer is extremely fast, you can see that a CPU that have 3.2 gig, right, is telling you gigahertz, is telling you that that cycle I showed you can happen 3.2 billion times in a second, right? That is what it means. So you see, this is very easy to understand. Okay, so let me take Intel because this is just Intel, so you can now if I use this Intel, nobody should confuse you with any other processor. So Intel, example, if you have core i9, this thing, you see it has 2. Okay, watch that 2, right? When you buy your system, the one you're going to see, I'm talking about, just focus on the thing in the middle, right? You have 3.00 and you have 5.80. When you buy your system, what you are going to see is that 3.00. They won't tell you about the 5.00 unless you are now. I'm now going and for you not to overuse it, they limit it to. So for Intels, okay, please, can I still be heard? I'm always seeing I'm seeing network signs on my screen. Someone should confirm that I can still be heard.
We lost you for a while, but we can hear you now.
Okay. Yeah, I saw memory computer stuff. So now okay, let me just recap it. Let's say when you buy your system, right? Look at it, focus on the thing in the middle. That's an example of an Intel it's an example of an Intel CPU or microprocessor. Okay. So what you see there, you see 2 things. They have 3.00 gigahertz. You equally see 5.8. When you buy your system, you are likely to see only the one on top. So for Intel, because I have used Intel, so they have 2, what they call processor-based frequency. Frequency is the speed, by the way, the number of clocking that you can have that can happen in a second. I've shown you an example of having 3.2 billion, cycle in a second. Now they have what they call max turbo frequency. Please don't tamper with your system after learning this thing. But it's good for you to know. So there are processors that you can go and overclock. They call that in overclocking. So what you are simply doing is to increase the capacity so that your computer will be faster. So, but you cannot increase it beyond the maximum turbo frequency. That's what I'm trying to say. This is the maximum speed that the processor can ever achieve in that system. You can see they give allowance for 2.8. Okay. So, but of course, when you buy your system, you're going to be seeing processor like 1.5. It's not going to be this high. All of these processors are very, very so I'm just using this as an example. Okay. So, but there are processes. I'm not going to teach you those processes because please, if you want to overclock your system, go and give it to a professional. Don't do it yourself. So, but I want you to know that some people don't know that it is possible for you to overclock your processor. So that's what I'm trying to say. Okay, now you can see I have given examples of Intel processor. You have something like you have terms like 7th generation. What does it mean? 4th generation core i7 core. This we are going to see the idea of core. Okay, in the next slide. So I'm going to break all these things down. There will be no ambiguity. You're going to understand it, right? But there's a note here that I want you guys to know. Please, because this is important for those who are going to be buying systems for their children, buying for yourself, for your family. It is important to compare the processor from the same brand and generation. Please, when you hear processor, okay, don't compare AMD and Intel. Okay, when you want to make a decision, always, for instance, in Intel, you know that you have heard of Core i3, Core i5, Core i7, right? Now, there are there are some Core i5 that might be better than Core i7s because people have actually decided that all Core i7 is better than all Core i5. So, first of all, you narrow down to the brand and then equally compare the generation. Okay, the 10th generation of Core i5 might be better than the second generation of Core i7. And people don't really understand these things when they are buying their system. So when you are comparing, please compare apple and apple and not apple and orange. Okay. So, but for us to now understand what those cores mean, right? You can see a typical process of machine cycle and how data flows in your system. You have your CPU, you have your arithmetic logic, you have your primary memory, and then you have your secondary memory. You can see. Don't pay so much attention. Don't cram it into what I'm trying to say here is that what is a core? Let's start with that. A core is an individual processing unit within the central processing unit of a computer. Okay? It is capable of independently executing instruction. Okay? Meaning each core can handle its own task. Now, task, I'm introducing the word thread for the first time. From now, you're going to be hearing thread. Thread is simply a singular task. Don't overthink it. Okay? Here is the breakdown. If you have a single core, right, it means it can do one task at a time. If you have a multiple core, example, dual means two cores, right? So when you buy, say, yeah, I'm buying a system of dual core, you say, waiting be that one again. It simply means that your processor has two cores. Other multiple cores, you can have quad core, octa core, right? Okay, it has two or more cores, meaning that it can. So you can see we have started developing this technology, and the technology is becoming better and faster because of some of these principles, right? So you can see if it is a single core, so you can know this simply shows you that you can even advise yourself on the spec of system you are buying just by attending this class. You see all those big this after this D, none of those specifications you see on Jumia can confuse you. None. Okay. You hear gigahertz, call this one, 5 gig RAM and everything. Don't worry. Let's go to the next system. Okay. So this is what we call block diagram of CPU. So to demonstrate the core, okay, sometimes picture speaks better than words. You see, if you have two cores, dual core, you can see the CPU that's showing two cores. If you have four cores, you can see the CPU showing four cores. If you have 8 cores, 10 cores, and so on and so forth. Okay. Each core contains its own ALU. Have you seen how I'm connecting these things? I have defined ALU last week. You know, there's no ambiguity here. There's no complexity here. So it has its own ALU, right? That is the reason why. So if I have 8 ALU, simple. What does it tell you? It means there could be calculation in 8 places happening at the same time. Simple. Multi, okay? Now, modern software and operating systems are designed to take advantage of the multi-core. That's why you can open different tabs, open different things at the same time. Because they are what they call sharing of resources. And that is what has led to what? What is it? Multitasking, multiprocessor. Right. Now, a four-core, right? Look at, we have given an example here with a diagram. A four-core, what's called quad core, can handle 4 different instructions or processes at once. Now, let us go to what we call hyper-threading. Hyper means more, right? In Intel, okay? And also, these people use simultaneous multi-threading. So Intel use hyper-threading, that's their nomenclature, but they all mean the same thing. You know, it allows each core to handle multiple threads, okay? Now, each core will handle multiple threads, meaning that tasks can even have sub-threads, okay? You're going to talk about thread very soon. Before we go to the next slide, look at the picture, okay, on the left-hand side. You can see a zero thread is handled by core 0. The second thread, which is thread 1, is handled by core 1. Okay, the third thread, which is thread 2, is handled by core 2. The fourth thread, which is thread 3, is handled by core 3. If we have additional thread, it goes back to core 0, which is the fourth thread. You see, thread 5 is handled by core. So you can see how these things work. So this is how CPU allocate resources, for us. Now let us talk about, I promise that we're going to talk about threading as well. Ladies and gentlemen, what is threading? The name threading, okay, I'm not going to use tax now because tax is different from threading. Threading, they are the smallest unit of program, just like you have bits in measurement of information. Okay, I'm going to talk about bytes later, but bits, we have met bits, 8 bits, 7 bits, all those boxes I was drawing. There are each of those boxes represents a bit. But when it comes to command, okay, we use the word thread. It's the simplest unit of program that can be executed independently. They are like lightweight processes, you see. They are not processes, they are part of the process, okay, with a program and share the same memory space. We are going to talk about it with the diagram that we have here. Each thread in the program has its own set of registers and stack, but share data and code with other threads. Multi-threading, of course, having defined threads. Multi-threading simply means what? The need for multi-threading arises from the increase in demand for multitasking and concurrency in computer. Concurrency means different things happening at the same time. Okay, the ability to execute multiple threads simultaneously has become paramount. Yes, see, you can't help it now. Every computer is not doing multi-threading. The technology has gone so far, and so this is what has led to improvement that we have today. So this diagram, okay, shows you a single thread will share what? The same register and stack, also the code and data file. But when you have multiple threads, so this multiple thread can be a single task that is divided to different single unit of execution. In that case, okay, the only thing the thread can have uniquely, if you check the diagram very well, is the register and the stack. But all the threads in a particular task will share the code because it's a task. It will share the code, the data, and the file. So each thread will not have its own just code, it have its own code. So that's what we call multi-threading. What is the advantage of multi-threading? Okay, the advantage of multi-threading is that it improves performance. Of course, naturally, if you have more things happening at the same time, just improve the performance. Resource sharing, you can see, instead of one thread being greedy to share, the code data and the files, you can have 10 threads sharing these resources as well. So it optimizes the operation of the system. Responsiveness, threads allows a program to remain responsive even when some threads are performing time-consuming tasks. What it means is that you don't have to queue, that's what we call responsive. You don't have to queue and wait. We are going to see different scheduling, by the way, okay, because it is very important in this discussion. So it's simplified programming. Written threads application can simplify complex problem by breaking them into smaller, manageable threads. Remember the time we are doing orientation, I told people to be careful about this whole idea of AI because at some point, AI is not going to probably do critical thinking, which is part of what we're going to talk about. The algorithms, it might write all the codes, right? But efficiency, for instance, you can have two bank apps that are doing, the thing is working perfectly well, but one might be more efficient because the programmer has gone beyond the level of just writing code of something that works. He's now even thinking about how much memory, how much compute resources does this thing consume? How can we make it like, these are the things that will make you, very good material for, programming jobs tomorrow. Because at that point, even if AI is helping you to write code, because I'm not telling you people not to embrace AI, that's not what I mean. But you are going to be a super user of the IT world if you are able to combine some of these, abilities. So I want us to look at the difference between multi-threading and multiprocessing, because these are the kind of things you are going to see, right? So it is important to distinguish between multi-threading and multiprocessing. Multi-threading involves multiple threads, right, within a single process. You can see a single thread and a single processor will have what? A thread, and it will share the code detail and the files, and also the register and the stack. But when you come to multiple thread, all the threads, okay, all the threads will be sharing the same resources if it is a single process. So a single process can be divided into two threads. So that process will have a unique code, data, and files, but each of the threads will have their own register and stack, register and stack, register and stack. But when you talk about multi-processing, you are talking about, code, data, files not being shared. Each process will have its own code, data, file, and will have what? Register and stack as well. So, and they will be running simultaneously. So you are having a single thread running simultaneously, and that's what we call multiple processor. Okay. So I need us to understand this. So this is where I'm going to be rounding off today, because if I go on and on and on, I want this thing to be bit by bit so that it wouldn't confuse all of us. So when we talk about the process, the state, and all that, this is where I'm going to draw the curtain today. Each process will be on at different states, at different. The idea of states means that at a particular time, remember all these things I'm telling you, it's not like they happen slowly or they happen very fast. So bear that in mind, okay? But we are slowing down time to be able to explain it. So just understand what I'm trying to do. All right. So it can be in the new state, it can be in the ready state, fetch, okay? It can be in the running, it can be in the waiting, it can be in terminated, right? Depending on this thing, on the particular phase, this particular, let me just take one single process now. If you look at it now, the process is created. Once you open your phone and start typing, you are creating something new. If you have your phone at rest, you are not touching it. Fine, nothing. If you are typing on your keyboard, you are creating something new. So when you create that, okay, is the keyboard will type it, is the processor ready? Okay, the control unit to be able to what? Get it ready. Getting it ready is similar to what we call decoding. Remember FDES, right? And then running, okay, is synonymous to what? Executing, right? When it runs it, sometimes it will terminate, but it is not all programs that actually will terminate. For instance, if there's a peripheral that you attach to your system, the program, when it finishes, instead of terminating, it will send the information to the IO. IO simply means input and output. So for those that are controlling drones, you guys saw what happened in Russia last week. Is it last week or this week? Yeah, Ukraine used simple drones, controlled this remotely using Internet of Things, and just went and detonated it in Russian bombers. Something like that. This is so you can see at every point in time, it is not a straightforward open loop kind of thing that just terminates. It's something that it is communicating every time, the coordinate, the GPS, and all that. So you're able to communicate steadily every cycle. You know the location of your drone, you can control it and everything. So sometimes when I talk about these things, it's not like, oh, it's different from what we are going to be doing or what we are going to be discussing or what you already know. No, you already know some of these things. You even experienced them. So it's not like putting your key card, on the door of your hotel and thing opens and then shuts. So there are some cycles that needs to continually interact. So what you're seeing in this slide that sometimes they need to continually interact with the processor. So sometimes it is not within, it could be peripheral. Remember, I said peripheral can be connected wirelessly or using wire. So when there is a continuous communication like that, that's what we're talking about. So um, now let's go to the next slide. You see, sometimes you have hold when this thing is being job schedule, balances resources, memory, and device. Remember the control unit. Now you will understand the importance of that control unit because you can see resources has to be shared. So you don't want to overpower the ALU. So depending on the power of the and the number of cores in the microprocessor, the control unit is able to, hold sometimes, get it ready, throw it into running, okay, and then from the running is finished. So you see, the scheduler is going to be the thing that is going to be in charge between ready and running. We're going to now have a slide that will talk of everything that happens between ready and running. Okay. So when it runs, that executes, it releases the resources that is used. The resources will become available for the next task. So what you see waiting there is if it is waiting to be to communicate with an IO. Anytime you see waiting, it means there's something outside the system that it needs to communicate to. Is it the mouse? Is it the router that's going to connect us to the internet? Is this the earpiece? Okay. In the case of phone, is it the AirPods? All these things happen. Again, I said very, very in a very fast pace. You have seen a case where we have 3.2 billion cycles running in a single second. I don't know how I can imagine that level of speed. So I'm going to end. Okay, this is 3:22. I'm going to end 3:30 today. So let me just so in all these things, there's a way it's represented, and it's called process control block. Okay, a PCB. There's another meaning of PCB, printable circuit board. But when I'm talking about processor, I'm talking about um this is actually a data structure, right? Okay, that contains detailed information about an individual process. Now, for individual processes, so when I talk about thread processor, it's not like it's not that simple. They have, a lot of things like memory address, okay, the command they are coming with. So these things are, are they scheduled or not? Probably like an ID card. That's the best way I can explain this thing. Are they ready to go and all that? So they come with that information and then they will meet the bouncer and submit their information. You'll be able to know, okay, this is where you go to. You go to the VIP session and all that. I think that's the best way to explain it. So first of all, you have to have an ID. That's the first one that is here. The process will have an ID. Because if every process can run anyhow, then the computer will be confused. Every single thread will have an ID, and that is how it can be identified in the first place. Okay, then remember I just mentioned states. Is the process, are you new? Are you running? Are you ready? Are you on hold? Right? So this thing, you can see how the coordination works. So the process state is important as well. Then the program counter, okay, is registered that stores the memory address of the next instruction to be executed what? By the process. So give me your program counter. Are you due for execution? I don't know. Let me see. Okay. That's why I'm using imagery to describe some of these things. Okay. CPU register. It typically contains the snapshot of what CPU register of the process. This register includes general purpose registers, something like saving and storing information and all that. So are you prior? Because some algorithms, you're going to see different algorithm of scheduling. You understand? Processes, they have different priorities. Okay. If you come to that point, you need to equally have this information. Okay. Then memory management information. You can see that this 1, 2, 3, 4, 5, 6 things. When you talk about trading processes, trading is not that simple. So this is what we call I mentioned the data and the stack. This consists of the stack. That's what we call now process control block. So that stack is shared, between threads. So each thread will have this information, and that's simply what it means. It simply means like you are attending an occasion. Give me everything about you. Okay, call it a biodata. I think I need to break this thing down so that it wouldn't be very difficult. Call it a biodata of every single process that is going to be executed by the processor. So I haven't mentioned it. The scheduling now, you can see now. Okay, let me use the diagram instead of reading everything that is on this slide. Just watch the diagram, right? You see the one, you see task 1. It starts, it is suspended. And task, you can see the timeline moving from left to right. Okay, task 2 starts and is suspended. This is what we call time sharing. Okay, this is what we call time sharing. Remember this thing again. Let me repeat again. It's happened in billion, like it's very fast. Okay, so we are actually, just imagine I'm slowing this thing extremely very slow before you can get this snapshot I am demonstrating using this slide. Task 3 starts and pauses. Now you see what happens. Task 1 will continue at some point. It will bring it back. When it brings it back, task 1 will continue and then it will pause it. So don't bother about so much write-up on this particular thing. I decided to put this graphic so that it will be easily understood. Okay. Now, let's go to the next slide. I'm rounding off for today. I'm almost there. I have 3 minutes to go. So, sorry. So, after type of scaling, what's next? Process. Okay. I'm rounding off already. I want to end. This is where I want to end today, so that the next time we meet, I'm going to talk about secondary memories and storage devices. So I'm talking about your flash drive, blah blah blah. How we started from punch card until we landed in the clouds today. We're going to talk about clouds because if you talk of, you need to tell the story how we started, because you can't just throw people into cloud. Oh, cloud computing, cloud computing. So this is what we are going to handle. Let me just go back to what we have today. So now, different kinds of algorithm. I'll call it algorithm because scheduling will come in different forms. How do you schedule? Right? There is what we call, these are different algorithms. So some of them are applied in different scenarios. The first one is first come, first serve. It's very common, of course. They call it something called FIFO. So please, those that are going to be doing cloud computing, these are sometimes you hear, oh, please don't joke with all these things. Not when you come to there's a topic in cloud computing, I think it's messaging or something, You see FIFO, which one be FIFO again? FIFO is the same thing as first come, first serve. So it's first in, first out. Okay, you can see the illustration. I have to bring some because sometimes illustration is better. So it means that you're going to be executing this thing based on first come, first serve. So the task 1 is going to be scheduled in the first place. The task 2 is going to be scheduled in the second place, task 3. So that's one. So I'm not going to be reading what is on there. I just want you to understand it. The second one is what we call shortest job, SJN, shortest job next. Okay. Now, if task 1 is very long, this is just algorithm. So I'm not saying this is the best. Task 1 can be a very long task. Task 2 can be a very short one. Task 5 can be the shortest. So for me, will I keep everybody waiting while I'm executing task 1? No. So there's an algorithm where it's okay, bring the short ones first, maybe we treat them first, you understand? Let's just treat them. Task 1 we treated. If the task 10 is the shortest one close to task 1, it enters. So they call it shortest job next, kind of scheduling algorithm. There's another algorithm which is called round robin. Round robin is equity. I will use that word. I'm using simple terms so that it will not be difficult for anybody to understand. Equity, I'm going to If people there are 5 tasks, you understand? I'm going to take the one from task one, thread two, round robin, like I'm going to take one, let it go round. No matter how long or how short the task is, I'm going to, that's what they call round robin. You can see that circle shows it, even though task one is the longest. Okay, what happens is that it throws the three in, the task two throws two in, and task three throws one in. But at the end of the day, I just look at what is coming out of that yellow box. I take blue, I take green, and I take the other one. Then I take blue and I take green. That one no day again. You understand? Next I will take what? The blue that is left. So that's all the kind of round robin. Then the last one, I already remember I mentioned in the PCB what priority is this task. Sometimes there are the algorithm that uses prioritizing. Okay, in this approach, each process is assigned a priority. It's not based on round robin, it's not based on shortest job next, it's not based on FIFO. It is assigned a particular priority, and the CPU is allocated to the process within the highest priority. So all the one with priority, you can have high, mid, and low. Remember, I am not the one doing this thing. Remember, the system has a way of determining the algorithm. So please don't overthink this thing. I'm not asking you to go and start trying to do priority. Of course, I have to explain it in a layman terms. You know what priority means. You know how you prioritize your activities and stuff like that. So that is the algorithm that uses that. So to round off for today, we have different, scheduling queue. This is actually where you are queuing stuff. You understand the job queue. You have the ready queue. The ready queue contains all the processes that are ready to be executed, but are waiting for the CPU to be available for them to be called on. The second one is job queue consists of all processes residing in the system, okay? Whether they are in the memory or on the disk, every single job. Then the device is when we are not talking about I/O. So things queue differently, okay? Within a system from motherboard, I've shown you buses, you understand? The buses that are carrying the data, the information, the instruction, and everything within the device, you categorize under the job queue. Ready queue are all the ones that have been assigned different kinds of either priority using the scheduling or FIFO or all those things. Then the device queue is when you talk about peripherals, you understand how you can connect with them. So I think I've mentioned this. So ladies and gentlemen, we are going to draw the curtain here. I have a hard stop. I've already surpassed the time by 3 minutes. I hope you enjoyed the class. This is very simple. Somebody say my system is dual core. At least you don't know what dual core means. It's not going to be this thing. So I'll hand over back to IK if you're still on the call.
Yes, I'm still on the call. Thank you very much, sir. Thank you very much, everyone. So, well, I believe you guys have learned a lot. At least I know I have. The few times I was listening, I think pixels. I got that one very well. Okay, so we'll meet next week, same time, same link. If you have questions and all that, of course, we have the DAIPODS channel on our Discord, so you can always ask questions there, and or you get the answer that you need. So thank you very much, everyone. The link to this class will be the recording rather will be uploaded on YouTube shortly, so you can just make sure you're following CodeCamp YouTube channel so that once it's uploaded, you get a notification. Okay, thank you very much, everyone, and do have a wonderful week ahead. Bye.